All right, so lesson 16 is on logarithmic and exponential functions. So maybe I should have done this before I did the logistic functions. I don't think you guys were a fan of the logistic functions yesterday, but you will like this because it will be very much a review from Algebra 2. All right, so it says the function f of x equals a to the x passes the horizontal line test. So a to the x we know looks like this if a is greater than 1, and it goes the other way if a is less than, like between 0 and 1. Therefore, it is what we call 1-to-1, and it has an inverse. So we can take the inverse of y equals a to the x, okay? So if you're finding the inverse of y equals a to the x, it's actually a logarithm, okay? So it ends up looking like, so logarithm function, it says for x is greater than 0 and a is greater than 0, and if a is not 1, then y equals log base a of x, if and only if a to the y is equal to x. The function log base a of x is read the log base a of x, and it's called the logarithmic function with base a. All right, so really that's the important thing about switching forms. I did b's before last year, but if you have something like log base b of x equals y, do you remember how to switch it? It's going to be b to the y equals x. Remember, I always did that little hand thing, like b to the y, skip over there, equals the part that's left. So you keep going, do, do, do. All right. Katie, do you have a question?
Can I just get one of them back?
Oh, you don't have one? Okay, so if we're switching log base a of x equals y, and we're switching to exponential form, all right, how would we do that? Yep, exactly. A to the y is equal to x. And if we have exponential form and we're going backwards to logarithmic form, that's the part that's a little bit harder. I always say the base of the logarithm is the base of the exponent. So if you have a base of 2, right, see how you have 2 to the 3, then it's going to be log base 2. Thank you. So I get log base 2 of x equals 3. All right, so then if I have log base 10 of, what is that, 100,000? Then I'm going to have 10 to the y equals 100,000. Is it 100,000 or there's, no, there's, yeah, okay. I wrote 6 there. All right, and then 4 to the negative 2 equals x. So how would we write that? Log base 4 of, yeah. So do you guys all remember that at least? You know how to switch forms. Oh, we're going to be so good then. If you remember that, we're golden. That's the main thing. All right, so we can solve basic equations. If I see log base 10 of x equals 3, I know how to solve that. I just switch forms. Okay, so I'm going to switch it, and it's going to be 10 to the 3 is equal to x. So we get 1,000 equals x. All right, if I have log base 16 of x equals 1/2, I rewrite it. I say 16 to the 1/2 equals x. Will, what's a 1/2 power? It's a square root, right? So we're going to have square root of 16 equals x. So x is going to be 4 then.
Do you not do plus or minus?
You don't do plus or minus 4 because that 1/2 is already like, it's telling you that you just have the square root. You don't have plus or minus. It's kind of like the principal root thing. Like if you have square root of 16 plus square root of 25, there's already a number in front of it. Plus, it can't be negative 4. If it was negative 4 and you tried to put that into your calculator, log base 16 of negative 4, what would happen? You cry. It would be an error, right? You can't take the log of a negative number. All right, so if I have log base a of 1 is equal to what? So a to what power gives me 1 is what we're thinking. Yep, exactly. It needs to be a 0. So a to the 0 is equal to 1. How about this one? So we have log base a of a to the x equals what? Because a to what power gives me a to the x? X.
I'm doing 3 or 2.
Number 3. I guess I went in a weird order. All right, log base a of a is equal to what? Because a to some power equals a. 1. And then log base a of x equals log base a of y. What do you think that means? X equals y, exactly. So if you have log base a of something, some number, equals log base a of another number, those two numbers better be equal to each other. Okay, that's what we're saying. All right, so a logarithmic function, as we said, is the inverse of an exponential function. So this first thing that's drawn is an exponential function. So this is like log, or it's b to the x equals y. All right, that's an exponential function. All right, so a logarithmic function is just the inverse of it. You can switch your x and y, solve for the new y. You end up getting this. This is log base b of x is equal to y. So this is really confusing for my students every single year because they're like, wait a second. But if I switch forms on that, it's b to the y equals x. And they're like, but that's the opposite of what that other one says, b to the x equals y. Why is that? Why are they the opposite of each other? Because they're inverses. And what do we do when we find an inverse? We switch the x and y. Does that make sense? So we've switched the x and y to get that inverse function. So don't get confused by that. The reason they're switched is because it's the inverse. All right, so things to notice about a logarithmic function. A logarithmic function, like the exponential functions that went through 0, 1, goes through 1, 0. And the exponential function had a horizontal asymptote. This one has a vertical asymptote of x equals 0. So it's going to get closer and closer to this line, but never cross. Now, this other one is not a horizontal asymptote. A lot of people think that on the right side of your graph, it's getting closer to something. It's actually not. It goes up to infinity. It just goes super, super slow. Because think about it. If I have log of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I have 10 zeros. So 10 to what power gives me that? Let's make it 11 zeros. 10 to the 11 is how we get that, right? So the log base 10 of 1 with 11 zeros is only the number 11. So see how slowly it goes? But it does go to infinity. It just doesn't go very quickly to infinity. All right, so this next one, so it says sketch the graph of f of x equals log base 2 of x. Okay, in order to sketch the graph, yes? Yeah, and that's why I was saying, like, we're graphing the inverse. So we switch the x and y to find the inverse. So find inverse, switch x and y. No, exponential function is like y equals, like f of x equals some number to the x, yeah. Oops. There we go. All right, so this next one. So it says, sketch the graph of log base 2 of x. And I said, remember, since f of x equals log base 2 of x is the inverse of g of x equals 2 to the x, it might be useful to pick values, x values that are in the form 2 to the x. So that's why over here I picked numbers that were like 2 to the 3, 2 to the 2, 2 to the 1. I want to pick numbers that are powers of 2. So let's think about that. If I have log base 2 of 2 to the 3, what do you think we get? Do you guys remember the rule that allows us to bring powers to the front? Nope. It is 3. We get 3. Right? Because it's log base 2 of 8. So Duncan was saying, is it 8? Not quite. Log base 2 of 8 is what? 3. So what do you guys think log base 2 of 2 is? Or log base 2 of 2 squared, I guess is. It's 2. That's right. So what about 2 to the 1? 1. 2 to the 0. 0. It ends up just being whatever that power is.
Sorry, 2.
Log base 2 of 2 cubed.
Oh, sorry.
All right, ends up being the power. Now, when we do a t-table, do we usually write things like 2 cubed, 2 squared? No. Like, I'm just telling you, the easiest thing to pick would be powers of 2. So if I was doing a t-table, I'd probably start with like 2, and then 4, and then 8, and I would think about it. So I'd be like, oh, I have log base 2 of 2. 2 to what power gives me 2? It would be 1. Oh, I have log base 2 of 4. 2 to what power gives me 4? It would be 2. So that's how we're ending up with those exponents. That's what we're doing. Okay? All right, so if I'm sketching a graph, I have 8, 3. I have 4, 2. I have 2, 1. I have 0, 0. I have, why do I have 0, 0? Now I'm confusing myself. 2, log base 2 of 2 to the 0. Yeah, that's not 2. That should not be a 0. That should be 2 to the 0. Sorry. That should be a 1. So it's 1 comma 0, because remember I have that vertical asymptote, so I was like, I have something wrong. I know. All right, so I have 1 comma 0, and then I have 2 to the negative 1. What's 2 to the negative 1?
1/2.
1/2. So I have 1/2 comma negative 1, 1/4 comma negative 2, and so on. So it looks like this. So if I did have 0 on my graph, it would be does not exist. You can't do it because it's saying what is log base 2 of 0? You actually can't take the log of 0. So it wouldn't work. All right, so use the above information to sketch the graphs of the following function. So what if you have negative log base 2 of x? So what kind of transformation does it do? Yep, reflect over the x-axis. Good. So we still have that 1 comma 0, but instead of having 2 comma 1, I have 2 comma negative 1. Instead of having 4 comma 2, I have 4 comma negative 2, and so on. So it's going to go along the y-axis, and then it's going to go like that. So we're just flipping it over. And then what about this? Log base 2 of negative x. So instead of having x values, we have negative x values. So what happens to it? No, reflect over the y-axis, right? So we're going to go, instead of having what we had here, we're going to go here. Does that make sense? So we're flipping it over. I don't ask you guys too much about reflecting logarithmic functions because I feel like you guys could always do a t-table if needed. But yeah, it is easy to kind of know where it's going, I guess. All right, common logarithm. So a logarithmic function with base 10. Usually we don't write the 10, so if you have a common logarithm, it looks like f of x equals log of x. Okay, so there's no base there. So it's really log base 10 of x. That's what we're saying, right? So if you don't see a base, it's assumed to be base 10. A natural logarithm is written as natural log of x. This is really, do you guys remember what base it has? Log base e. Okay, that's what a natural logarithm means. I don't know why they do that, why they just can't write log base e, but less to write, I guess. Allison. All right, so properties of natural logarithm. So I have natural log of 1 equals blank, because what? So think about what we're saying. We have log base e of 1 equals something. So if I switch to the other form, I have e to something equals 1. What does it have to be? 0, right? So natural log of 1 is always 0, because e to the 0 is equal to 1. How about natural log of e? What do you think that is? 1. Yep, because natural log is log base e, right? So when I switch forms, it's going to be e to the 1 is equal to e. How about natural log of e to the x? Right? It's log base e of e to the x equals something. So e to something equals e to the x. It has to be x. So that's why when we do these problems, natural log and e are going to cancel, right? You end up just having that power. And e to the natural log of x, likewise, is also x. And then if natural log of x is equal to natural log of y, then we can say that x equals y, exactly. So hopefully these are all kind of review for you. So we'll go quickly through these ones. So it says evaluate the expressions without a calculator. So if you remember when you guys had your Algebra 2 logarithms test, half of it was without a calculator. Okay, it's important that you guys know how to do this without a calculator, especially as you're approaching standardized tests, PSATs, SATs, and so on. I think the SAT actually gave a calculator. All right, so evaluate the expressions without a calculator. So if I have log base 3 of 3, so we're saying 3 to what power gives me 3? If you want to write an x, like some of you guys liked doing that last year, that's fine. You could say log base 3 of 3 equals x, and then switch forms. 3 to the x equals 3. What does x have to be then? 1, exactly. All right, so be active note takers right now. Try these problems along with me. All right, so this one, if we say equals x, then we have 3 to the log base 3 equals x, and we want to switch it back to logarithmic form. So think about that. If you have 3 to something, let me do another example. Let's say I have 3 to the 2 equals 9. I would do log base 3, right? The base of the logarithm is the base of the exponent, of 9 equals 2. Do you see how it works? 3 to the 2 equals 9. Can we use that here? So we're going to do log base 3 of X equals the power. Log base 3 of 8. So what does that mean? Yeah.
Very confused on what's going on.
What do you mean?
Like at the bottom, how do you get to?
I'm just switching forms. So 3 to the 2 is equal to 9. Do you remember how to switch forms? So if I have log base 4 of x equals 2 and I switch forms, I get 4 to the 2 equals x. Right? That's all I'm doing. So I'm saying, like, here's an example to help us with this other one. So we end up getting x equals 8. Okay, now that's hard to switch forms. You guys never have liked switching from exponential back to logarithmic. That was a difficult thing to do. So what's the easiest way to do this problem? Guys, not ignore it. Right, if you have 3 to the log base 3, what do you notice? The 3 and the log base 3 cancel. It just becomes 8. If you guys know that one, it saves you a lot of time. So if I give you something like 7 to the log base 7 of 4, what is it going to be? It's going to be 4. So every single year I put this on the test and people will mess it up because they don't know that basic rule. So you can make little flashcards or whatever for logarithms. It's very useful. So we end up just getting 8. All right, how about this one? So we have log base 9 of 81. Can anybody do it in their head? It's 2, exactly. So what you're saying in your head, you can write it's equal to x, and you can think about switching forms. But you're basically in your head saying 9 to some power gives me 81. Right? 9 squared is what gives me 81. So it should be 2. Okay, this one's a little bit harder to do in your head. It involves a fraction. So let's go ahead and do the x thing. So we're saying 9 to x equals the square root of 3. It's tricky. Does anybody know the fraction? It is 1/4. Good. It's 1/4. Now, most people cannot do that in their head at this point in time. I think later on you guys get better at it. But what I would recommend doing is, if you remember, we've talked about getting things to be the same base. Like the square root of 3, I can write it as 3 to the 1/2. What about 9? It's 3 to the 2, right? So we have 3 to the 2 raised to the x. So we end up getting 3 to the 2x equals 3 to the 1/2. So that means that we can set our two powers equal to each other. We can say that 2x is equal to 1/2. So when I divide by 2, I get 1/4. That's probably the easiest way to think through those problems. Okay. Does it make sense? Like if you take the square root of 9, what do you get? 3. If you take the square root again, what do you get? Square root of 3. It was a square root of a square root, so it was a 1/4 power. Raise the 1/2, raise the 1/2 again. All right, other properties of logarithms, you guys probably kind of remember these. The product property. It says that if you have log of a times b, it is not log of a times log of b. What is it?
Plus.
Log of a plus log of b, exactly. And the quotient property says if you have log of a divided by b, it's going to be log of a minus log of b. And the power property, if you have log base, well, it can be base anything. We'll say log of a raised to the m. It's going to be m times log of a. Okay, and those logs could have any kind of base. You could put a little base of b or something next to them. So the power property says you can pull powers to the front. Okay, do you guys remember why that's true? Why you can pull powers to the front? Like if I had log of 7 cubed, right? It's really the same as log of 7 times 7 times 7, which with your power property or your product property, you could break apart into 3 of the log 7s. That's why that works.
Is that a minus?
Yes, it's a minus. All right. So it says, be careful. Many people think that the product rule is log of a plus b equals log of a times log of b. They get them confused. Okay, if you ever get stuck, just think about the logs that you know. Do you guys all know log of 10? Log of 10 is what number? It's 1, right? Log base 10 of 10 is just 1. 10 to what power gives you 10? Do you guys know log of 100? Nope. 10 to the 10 is not 100. 10 to the 2, right, is what gives you 100. So always think back to those. So if you have log of 10 plus 100. That's the log of 110. Do you guys know what the log of 110 is? Nope, no idea. You would have to use a calculator, right? So is that the same as 1 times 2? Not even close, right? So you can always think about the ones that you do know to help you with the formulas. That will be really important as you have a standardized test because they're going to trick you with the multiple choice. They're going to say, which of these are true? And you're going to be like, what? Which one is true? I don't know. So use things that you know to figure it out. All right, so evaluate the following logarithmic expressions without a calculator. So if you have log of 2 plus log of 5, how can I write that? Yeah, exactly. It's log of 2 times 5, which is log of 10. What is log of 10? We just said it's 1. All right, the next one. So if I have log base 4 of 192 minus log base 4 of 3, it's going to be 192 divided by 3, which is log base 4 of, do you guys know that?
64.
64. So what we're saying is 4 raised to some power is what gives me 64. 4 raised to what power? 3. Exactly. You could off to the side do 4 times 4 times 4 if you need to. All right, this next one has subtraction and addition. So I'm going to start it out, I'm going to have log base 2, and I would start out, I have 6 over 15, right? But then all of a sudden I have this plus log base 2 of 20. So you could actually do all of those in one step. Anything that has a plus in front of it, it's going to go on the numerator. Anything that has a minus in front of it, it goes on the denominator. So it would really end up being log base 2 of 6 times 20 all over 15. Right? Because the 6 and 20 had pluses in front of them.
So log 2 will be 3.
Log base 2 of 120 over 15. So Ian's saying that that's 8. So 2 to what power gives you 8? 3. Ethan, are you getting better at those? Can you do it in your head now? Okay. All right, how about this next one? So you could bring the 1/2 up as a power if you want, or you can just leave it out front. So if I have log base 2 of 16, can you do that part in your head? 2 to what power gives you 16? 4. So you have 1/2 of 4, which is 2. So what if you had brought it up as a power first? What if you had 1/2 of log base 2 of 16 and you brought this up as a power? What does it mean to have 16 to the 1/2? It means the square root of 16, right? So you have log base 2 of the square root of 16, which is log base 2 of 4. What do we end up getting? Same thing, 2, right? 2 to what power gives you 4? It would be 2. Okay, so can you guys, are you getting better at doing those in your head? Yeah, it's all coming back to you, Christian. All right, so how about this one? All right, so this one I have log base 3, and let's go the other way. We have the 4th root of 27. So what power is 27 raised to? The 1/4 power. That's what a 4th root means, 1/4. That's how you put in 4th roots in your calculator. That's the easiest way. So we're going to bring this 1/4 to the front. So we're going to have 1/4 times log base 3 of 27. Well, how about the log base 3 of 27? What's that?
3.
Yeah, 3 to what power gives you 27? It would be 3. So you have 1/4 times 3, which is 3/4. All right, the next one, I have log base 5 of 1 over the square root of 125. So I have log base 5, I have 125 to the negative what? 1/2. Why is it negative? Right, because you have the 1 over. Okay, so we bring the negative to the front. So I have negative 1/2 times log base 5 of 125. Do you guys know what log base 5 of 125 is? It's 3, right? That's all right. Everybody says 5 over here. So you get negative 3 over 2.
Well, you would multiply it 5 times 3.
Yeah, to get 25.
Sounds bad.
All right, how about this one? So I have log base 1/2. Oh, base 1/2. Of 1 over 16. So if you want to rewrite it so you have it equal to x on this one, it might help. We have 1/2 raised to the x equals 1 over 16. Does that make more sense when you see it that way? How many times would you multiply 1/2 by itself to get 1 over 16? 4 times. That's your answer. All right, and the same idea here. So I have log base 8 of 2 to the 1/2. I bring the 1/2 out front. And then you're like, ugh, log base 8 of 2. Yikes.
1/3.
It is 1/3. So if you need to rewrite it, I would recommend doing that. If you want to set that part equal to x, you can do it off to the side. And you can say 8 to some power equals 2. Oh, whoops, I didn't mean to do that. It's not 1/2. 8 to the x equals 2. So you rewrite it, and then you have to think about it. So if you get stuck on these, a lot of students have trouble with this. I tutor people all the time that have no idea how to do this problem. And you know what I tell them? I tell them to get it to be the same base. So if you have 8, rewrite it as 2 cubed to the x equals 2. 2 is 2 to the 1. You end up getting 2 to the 3x equals 2 to the 1. So that means 3x is equal to 1. So you get x equals 1/3. Does that make sense? So if you cannot do it in your head, you got to kind of do that extra step. So I have 1/2 times 1/3, which is 1/6. How much more do I have? A little bit more. All right, we'll stop there with the expanding right now, and we'll do the rest tomorrow.